All right, welcome to the July 6, 2019 Social Modeling Video Conference. Topic this week is, or this month actually, is interface between ontology engineering and structural modeling. This kind of came up, this topic came up on reviewing a book on ontology engineering, Introduction to Ontology Engineering. It had some very well, it was interesting similarities between the logical properties associated with structural modeling activities and then some of the ontology um, languages, description languages, and also the reasoners that support those languages. So it was kind of an interesting topic. So I'll go ahead and discuss that just a little bit more. And so the goals, given this newly found connection, is to explore the application of ontology-based description logic reasoners to structural modeling tasks and processes, and then detail similarities between structural modeling elements, the AMEI and the ART, and the description logic reasoners, and based on the associated logical property groups. So essentially, what we've done with the structural modeling work is put together an approach that is outlined in 27 logical property groups. And those groups can be associated with certain natural language relationships. In the work on the introduction to here it is in this book, The Introduction to Ontology Engineering. We just picked one specific natural language relationship, which was the proper part of, and then they aligned it with the following logical properties, which is reflexive, transitive, asymmetric, and irreflexive. And you see that antisymmetric is not supported across during the description logic. And this was then very interesting that we have the features or the logical properties and then the languages, and which logical properties are supported by which language. So just quickly looking at this and not really going into any detail yet, it seems like what we've been doing in the logical properties with the structural modeling is associated with this group called DLRU, which is what they call a unique or a peculiar type of description logic. But it's reflexive, and it's it does not include anti-symmetry. You don't allow anti-symmetry. Transitive, asymmetric, and also irreflexive. But it also is acyclic, so that it basically doesn't allow cycles. And I'm not quite sure about the cyclic part here with these other reasoners. I need to really dig into that a little bit more. Look at that. But the component parts that go with it. So anyway, based on the associated logical property groups. And the primary advantage, I believe, to the structural modeling is that it provides kind of a structured front end to ontology development. And that structured front end has some advantages. But the logical reasoners and the description languages, they also appear to have some benefit once you have developed the structure. Because what we know is what we've shown in the, bring this other, oops, I got to bring up another chart here, share a different one. Let's see this one, share this one. So, hope everybody can see that. But in the, what we found is that in the single-threaded, asymmetric, irreflexive, intransitive type of approach, where you can see in the single thread over on this side, is the structural modeling software that we have now can handle that. And that we call that a global type of relationship. But if we have like part of, now part of could be global like this, but it's not restricted to it. So when you have multi-threaded, which has local relationships, the classical structural modeling software cannot effectively reproduce these structures. It seems that what can happen here is that once we develop these structures, then we can use the description logic reasoners to validate those structures and also integrate structures that have been done at different times, so that it really provides another step forward. What the description logic reasoners appear not to have right now is something that does clustering, so that within the symmetric components, I'm not quite, that of course needs to be checked out, but the idea that we can use the reasoners in the local types of integration is, I think, very important. And the idea that we could use the structural modeling techniques as a front end to the application of the description logic reasoners is also, I think, really an exciting idea. So with that as an introduction, are there any questions? Okay, all pretty clear then? All right. So, so say we have used the structural modeling approach and we've developed a couple of structures. Then we could use the description logic reasoners to integrate those two different structures and see if they're consistent. We could also use it for instance checking, and once you have this encoded into a kind of a knowledge base, you can also use instance retrieval. And you can then look at different concepts. So I think it really opens up another way of looking at structural modeling software, and another avenue of open source code that can be used. There's a number of open source types of reasoners out there right now that you can use. Again, the description logics are a family of formal knowledge representation languages. what we do with structural modeling, of course, is we're developing knowledge, and a structured knowledge about what the current situation is. And once we have it in that format, we can use these services provided by reasoners to actually look at different components. So we can integrate and validate structural models that have been developed at different times. And I think this is one thing that was a little frustrating in the past. If you put a lot of effort into the developing a model, then it was difficult to integrate them unless they were a very specific type. It was possible to, to develop and integrate global, irreflexive, asymmetric, and transitive relationships. But the ones that were local, like a typical part of, you really couldn't do that. So you could do it, but it wasn't repeatable, and it wasn't stable. So this particular approach allows you to do that. So if you have 3 or 4 different groups that are working on structural modeling techniques, they all develop like a part of structure, then you could use these reasoners to integrate them repeatably. You could have a repeatable type of integration. So, and that to me is very exciting. And even more than that, if you look at the natural language relationship part of, we can abstract that back to the logical property group. Say, oh, well, we're working with irreflexive, asymmetric, and transitive relationships. So if you say influence or impacts, and assign it irreflexive, asymmetric, and transitive, then you can use the same type of reasoners for those natural language relationships. If you have numbers of those developed in different groups, then you could use the reasoners to actually integrate them and address large number of logical groups in a repeatable fashion using these reasoners. And so that's, to me, a great advantage that using these techniques in this specific class would help. Okay. So where to begin? Okay, so here this is a kind of a newer book, and it's actually an open source book on ontology engineering. And looking at it, there does appear to be a clear interface between structural modeling tasks and description logic tasks. And this point right here, I think, is quite an interesting way to look at it. And structural modeling can serve as a structured front end to ontology engineering tasks. So when you're working with a group of people, this again provides a more structured approach to the ontology development. And as I mentioned earlier, the classification components, the idea of putting things into classes or categories, doesn't appear to be directly supported by description logics, but it's supported by structural modeling. And that way, structural modeling seems to be an overarching, have a broader approach, but these description logics could be brought in and applied to the specific types of natural language relationships for which they relate, which they're in the proper logical group. So anyway, the description logic is provide a set of open source tools that expand the scope of repeatable and verifiable system structures. So I think that's very exciting and pathway to check out and look at. And here again is the, well, this is just for properties of parthood and properties of proper parthood, which would be, we're looking at reflexive and irreflexive here. So proper parthood is irreflexive, and they're saying that parthood is reflexive. And so in either case, you would have, you would not have, well, let's back up on that. So if you had a part of natural language relationship that was proper, the proper parthood, then it would be irreflexive, asymmetric, and transitive. That's one logical group. You had one that was just parthood, that was reflexive, asymmetric, and transitive. That would be another logical group. And then if you mix them both together in the AMEI, what you would have the non-reflexive, asymmetric, and transitive group. So from just these properties, you could actually do 3 logical property groups and have different, and look at it with different reasonings. So the reflexive would have the AL2 description logic, which is right here, these guys, oops, AL2 right here. And then here's our AL2 query language. They do reflexive and irreflexive, so they would cover everything. However, the query language is not transitive, so that wouldn't do it. So we just have to have the AL2 description language would cover, but it also allows cycles. I'm not sure. I think it would also apply to acyclic types of applications, but we'd have to look at that in more detail. But this TLRU appears to be the one that most closely aligns to the type of logic that we have now. So, and of course, there's some of the earlier charts Mary and I did a few years ago, and we looked at the number of different types of relationships and sets. And of course, this was the early basis for the AMEI. Then we just talked about the different properties across those. So an ontology appears to be a special kind of structure. So we can, I think, look at those ontology tools that are available, especially the reasoners, and see what we can use in the structural modeling applications to help support reasoning. And of course, need to locate and evaluate open source code for acceptable description logic reasoning. So that's about my overview of this. Are there any questions, comments, ideas?
Yeah, Joe, could you go back a page?
Sure.
And remind me what the sets are?
Oh, here?
Yeah, what are these set relations?
Yeah, so these set relations. A system is just 2 or more objects, but the structural relationships mapped over each object set, right? So the set ID, this is just an ID number. It's any non-empty set. And what it is, a specific relation is equivalence, right? So we say, oh, one object is equivalent to another. So I have a set of equivalent objects. And then the next one here is, not equal, subset of, proper subset of. These are the relationships that go with these IDs. Maybe we can, I'll pull up a different chart here. Somebody else also talked about a while back. Let's see. maybe it'll be a little more. Let's see. Can everybody see that chart? The logical relations.
Yes.
Yeah.
So we did this one a few years ago, and so we took these, basic single logical properties, and then mapped, how they were combined, and then how their names changed, right? So that here's the equivalence, here's the strict order here. And so these are the ways we could be grouping the sites. So,
Joe,
yeah,
I mean, is it the case that implied in what you're presenting there with first you had things, the relationships of properties in first order logic. Actually, first order logic is just a constricted set, a constricted choice among those properties depending on which system you're following. And then you have set theory, which is different than first order logic, right?
right.
And then, I'm a bit fuzzy on my history of mathematics and logic, but it was like 120 years ago or something, right? These guys were trying to demonstrate the mapping of set theory to logic to the other maths and algebra,
right,
like
sure.
the Hilbert program and these types of things. And they, on their path to doing that, they got upset by Gödel, right? In some ways, Warfield was trying to celebrate that back when he was, showing the the complementarity or interchangeability of Boolean algebra, binary matrices, logic, and set theory. I mean, he tried to use present all these things kind of as a mapping from one to another. And it's my understanding that people hadn't really been doing that. He wasn't completely unique, but moving between all of those was an unusual thing, and it was useful for applied work. But the people that had been doing this mapping between logic and set theory and all that, they were real pure mathematicians and logicians and set theorists. And then they kind of gave up. And then 80 years later, Warfield found, some reason to look at the confluence of those for applied purposes.
Yeah, that's a really interesting point, Kevin. And I would say that there's a key concept involved, and between like Gödel's theory and the incompleteness theorem and Turing's work, right? And also Warfield's work. And Turing's thesis has a component in it, which he talks about Gödel's work, and he says the proof, the proof of Gödel's work is the kernel or the shell or the foundation for its solution, right, of the incompleteness theorem, because what it says is essentially that there's an infinite number of representations, all based on the previous representation. So the incompleteness theorem says, oh, this is incomplete here, but if I take A as incomplete, then I can use that incompleteness and add to it because I've described what's incomplete. And then I do the next part and, oh, okay, and now I know more, and then I've added the next incomplete. And you're right, Warfield actually talked about that a little bit in one of his representations of adding to and creating. And it's I thought about that a couple times. I just can't pull it up right off the top of my head because I haven't looked at it in a while. But you're right. He basically talked about that, and I think he might have talked about and referred back to Turing's work because Turing does talk about that in his thesis, in his dissertation. That fact that the incompleteness theorem is just the foundation for the solution of the next incompleteness theorem and the next one and the next one and the next one, and they just build on each other. So they're never complete, but you can always expand them to the next level. That make any sense?
Yeah. The mathematicians and logicians from a century ago, we're looking at the total systems and, the existence of systems and the possibility of systems and that type of thing. And, they created a lot of, machinery, and most of it's not been used in an applied way. In my narrow or my shallow view of it, but the Warfield did try to use the integration of these views, which you don't typically see. I mean, I haven't seen it in too many other people's works. This, fluidity between logic and set theory, and
yeah, it is not. It's not a common approach, but I think the idea, the value of this is going and is translating from the natural language to the formal language. And what that does, that activity of translating or going from informal language semantics to formal language semantics and computation, going toward the formal component really provides tools, intellectual tools and logical tools for computation that help people get a better grasp on complexity that's completely beyond their natural ability to comprehend with natural language. And so you really have to go both ways with that. Once you look at what you've computed and what those formal semantics are, then you can go back. So I think the challenge there is to expand the areas where that translation from natural language to formal language is more repeatable, is more valuable, and is understood by a greater group of people. If that makes any sense.
yeah.
And it's just, I'll present this again. So one of the key ideas, of course, here, just in talking about the the natural language groups, where you have the idea of a natural language relationship that's either local or global, right? And that has an impact on how you can use it for reference, and how you can do the computation. So the key part that I found is in the published work, people have published the the computations for the structural modeling, all of the examples were global. But most of the applications that we saw and reported today were local.
Where were the examples global?
No, the global, that was in the handbook where they get the appendix on the software, on the
Yeah.
menu software. So it's like greater than, heavier than.
Yeah.
Those things were all linear, ordered, strictly ordered, and global, right?
Yeah.
And so when you have that type of software, then you try to apply it to ones that are local, like part of. It doesn't have the logical inference, right? And so the key there between these two pieces, right, is saying, oh, okay, well, if you have a global relationship, then you just have to get all your data from empirical data, right? You just have to ask people. You really can't infer. But that's kind of like an ontology, right? You develop an ontology by asking people, right? You ask them how things are related and you develop this structure. And so in the part where it's local, you say, okay, fine, this is local. We'll get the information. We'll put it into the structure. But once we have this structure, then we can use the proper kind of description logic to validate it, to integrate it, to add components to it, right? So say I have a large local structure that's part of, and someone wants to modify it, right? Well, under the current structural modeling or the classical structural modeling software, you'd have to go through and do that all empirical knowledge, right? But with a description logic reasoner, you can actually, it appears anyway, that you can actually validate that. You can have a large structure and then you can validate that large structure using the proper type of reasoning.
Do you think that you could use description logic as the structural modeling database?
Well, um, um, so a reasoner, a reasoner actually works on databases, right? Like a Sparkle database or a knowledge base. So that's kind of two different things. But yeah, if you had if you created a structural modeling database that said, oh, this is how all of these objects are related, large matrix or knowledge base or whatever, had that all encoded, then the plan would be to use a reasoner to verify it. And
Wow.
let's say I have done a lot of work and I've got this structure, let's say it's got 50 or 100 elements in it, right? And then I want to modify it. I want people to look at that. I want to modify it in different ways. So then you take that empirical knowledge, you bring it in, but you can use a reasoner to validate that. Or if you have two different, part of structures, right? There's a lot of different ways that you can use these reasoners to expand the application of local types of relationships.
So for your implementations, how would you get a structure into a description? I mean, into a one of the databases you mentioned, or is it in a database like that already?
Well, yeah. So okay.
In other words, can any of these description logic reasoners read a structure that you would produce from the software that you've developed so far?
Yeah, I think. Well, yeah. Let's think about that for a minute. So, I mean, an ontology is simply a structure, right? And so you can, and and it's a structure that's related by certain logical properties. So that's really a good question. But when we look at, and let's just go and look at this for a second.
Well, the ontology, compared to the way Warfield and Christakis implemented their structures,
Yeah,
an ontology goes in a few additional steps into labeling the nodes with a typology and the relations with a typology. When they say what is the nature of the relationship represented by a 1 or a 0 in Warfield or Christakis's matrices. They didn't assign anything. They just had 1s and 0s, and you kind of the people that were using the software just waved their hands over it and said, okay, in this instance, the relationship means priority over, but in this application, it means precedence, and in this application, means part of, or whatever. But that was never in the representation in their software.
okay.
Whereas I think the ontology databases, they say what is implied by this asserting a relation. It's not just a relation, it's like a part of relation or a precedence relation, right?
So again, I think that I think you're right. I think that all of the standard ontology tools, right, that are available now have a number of components. Now, the reasoner is just one of those components, right? And so, and there's different reasoners that can be plugged into different ontology development tools. And so, like, are you familiar with Protege?
I've heard of it because I've read about ontology work, but I'm not that familiar with it.
Okay, so I went through and I looked at a few things. Let's just take a little look at this. Look at the search here, ontology. All right. No, I'm going to just stop presenting this. Bring this other one up over here. Yeah. Okay. All right. Let's be able to see that there's a lot of ontology tools available. And I just went through and looked at some of them, right? And I'm looking basically at the open source ones, but I'm also scanning here to see if I can find a reference to so like here's a here's a Fluent editor, right? So this essentially it supports Swirl and a number of other things, but it just seems to me that these components and these types of tools would be able to support structural development. And that's as far as I've gotten so far, right? I'm just thinking, okay, how would that work? What would you be able to do? And it says it's interoperable with Protege, and of course this one has a R language package and a number of other things, right? So, but there's tons of them out there. And I don't know if anybody had looked at that specific aspect before, right? Have you ever heard of anybody looking at using ontology tools to create structures?
With the software that we use, no.
So that's so mostly what it appears to me in ontologies have an expert with a tool, that works with a group, and then they develop some kind of ontology development of structure, right? But with the collaborative approach, where you have groups of people, like in structural modeling, then it would be a little different, right? You'd have the structural modeling activity first. It creates the structure, and then the structure goes into the ontology format. What that means and what tool, I'm not sure of yet. And would need to look at that, figure that out a little bit more. So anyway, that's as far as I've gone with it. You think this has any, provide any benefit?
Well, I thought for a long time that we have a good tool for inquiring about the development of an ontology.
All right.
In a group, when you're in a domain where there isn't an expert, where you have to draw on multiple people, or where the the relationships are opinionated, and whether they exist or not, or intention rather than.
Yeah. So anyway, that's kind of triggered my mind. And
Some puppets, for example.
Yeah.
When you.
So I think it's kind of exciting. Actually.
Talking about plan and do doesn't actually exist. It's just your opinion and your preferences of what you want. It's about precedence between things. You have to do some things before other things, but some of that depends on what you would prefer to do, because it has other effects than just the following action. So I think it extend planning that it's not necessarily used for right now.
Yeah, so I think that, I agree. I think it's has some potential. I'm trying to figure out a small, simplest way that you could kind of create a structure using ontology tools, and then evaluate different reasoners.
Mm-hmm.
I'm not quite sure what that is, but it's, I think, an interesting approach. Of course, Protege has a lot of different ways to deal with things. So use Web Protege, right? Okay, there we go. That might be something that would be interesting. Okay. Not coming up really fast right now. Yeah, okay. Take a look at that later on. Anyway, that's kind of something that I think would be, of course, in the Introduction to Ontology Engineering book, the woman that wrote that talked about why they had so many different types of description languages. And most of those were for scalability over, like internet scale searches and logical operations. And the more logical properties you add, the more complex the computation becomes. And I think one thing about working with groups and developing an ontology within a group, you really wouldn't have to worry about web scale logic, because you're probably, in most cases, you're going to have less than 1,000 nodes. So that would be very easy for modern, almost any modern computer to handle. We're not talking about millions or billions of nodes like you would have searching and looking at on the internet. So I think it's kind of for the smaller scope of a structural modeling activity, the restricted number of nodes would open up a way for almost any of those description languages to be used. All right, well, let's see. Any other comments? So we'll go back here and find the original. There we go. All right. So anyway, yeah, next steps. So is there any, have you had any experience at all with, I haven't really had any experience with these, and I think I'm going to get some time. I'm going to look at, maybe do some work with them and see what I can figure out. You be interested in participating in something like that, Kevin? That's about all I have for today. Is there any more comments, questions, activities?
Joe, I wanted to mention that we, in error, included an earlier version of Chart 9 in this, and we'll update it and provide an updated version of Chart 9 when we send it out.
So which, this one or
Yeah, no, next one.
this one?
The one with all the plus this one, right?
Oh, okay.
Yeah.
This one.
Not that one.
Okay. Is it before or after this one?
It's after that one.
This one. Is it after, before or after, is it after this one?
After this one.
Okay. This one. Is it after this one?
Yes.
Okay. Is it this one?
Yes. Sets, relations, and what is it? Yeah.
Okay. Cool.
So we'll update that.
Excellent. Before we send it out. All right. Great. Well, Kevin, is there anything you want to present in a couple weeks? Okay, so let's see. Pulling up the calendar here. So August 3rd will be the next, be the first Saturday of August. So see if that, hold that open. Then there's September 7th. And we'll kind of hold that open, see how that goes.
I noticed that Kevin started typing something, and then I think that he intended to type that his system hung up.
Oh, okay.
I don't think he's able to either respond or sign off.
All right then. Well, we'll kind of communicate with them a little later on and see if we can do something for the next round. That will sign off for this broadcast.
Thanks, Jeff.